Okay, thank you, Michael.
Thank you. Okay, good morning, everyone. My name is Michael, and for my project this summer, I worked on updating models for Great Lakes ice cover climatology and interannual variability under the mentorship of Dr. David Cannon and Dr. Jiao Wang. So as a quick introduction to myself, I am a fourth-year undergraduate at Boston University, pursuing a Bachelor of Arts in Marine Science with a minor in Earth and Environmental Sciences. That said, although I go to school in Boston, I was actually born and raised right here in Ann Arbor. So in the process of working here for the summer, I've also been spending the summer at home. So to start, as an overview of why Great Lakes ice cover is important to study, the main reason as it relates to the scope of this project and the Great Lakes Basin as a whole is climate change and resilience. Global climate change has led to increasing air and water temperatures as well as extreme weather, which have resulted in poorer conditions for ice cover in the Great Lakes. Likewise, ice cover can be affected greatly by larger scale atmospheric teleconnection patterns, such as the El Nino Southern Oscillation and the Atlantic Multi-Decadal Oscillation. So Great Lakes ice cover serves as a regional indicator for larger trends in climate change, and as a result also serves as a valuable tool for climate resilience. So ultimately, the purpose of this project is to determine the overall trends in ice cover over the entire extent of our current data to be used in future climate studies. Daily ice cover data is sourced from the National Ice Center and spans 51 years in total from 1973 to 2023. Ice cover typically occurs between November and early June, and for the purposes of this project, all ice cover data is presented in the form of percent ice cover, meaning the percentage of a lake's total area in which ice forms. For this project, we observed ice cover trends through 4 distinct analyses. Ice cover duration is simply the total number of measured days of ice cover each year. More specifically, it's the difference in days between the first and last date of ice cover. Climatology is the mean ice cover for each day of the winter season across all years. In that sense, it's the average progression of ice growth over the course of a winter season. Annual average ice cover, or AAIC, is more or less an inverse of the climatology. It's the mean ice cover for each year, averaged over a set period of days. And for this project, we use December 1st to April 30th as the date range to represent the general period of ice cover each year. And annual maximum ice cover, abbreviated to AMIC or AMIC, is the maximum ice cover of each year. So in effect, it takes into account the single highest ice cover value observed for each year of data. One additional thing we experimented briefly with was climatologically filled data, which is essentially a method for filling in missing ice cover observations in earlier years using the climatology. Jessica's presentation will be right after mine, and her project employs this much more heavily. So she will be going much more in depth into the methodology of it than I will here. And lastly, all trend analyses in this project use linear regression to fit data into linear equations. You probably recognize the equation there, y equals a plus bt, where a is the intercept or initial value, and b is the rate of change over t, the variable of time. So here we have the climatology for all lakes based on biweekly averages over the entire 51-year period. The dotted line there represents our 10% ice cover threshold that we use to calculate the first and last days of ice cover, and by extension, the total duration. And based on that, you can see that on average, ice forms earliest in St Clair and latest in Lake Ontario. And likewise, ice cover is always highest in St Clair since it's the shallowest and smallest of all the lakes, and as a result doesn't take too long to freeze over. Based on the 10% threshold, if you look at the spatial distributions for ice cover duration in just the last 2 winter seasons, you can see that 2023 was an extremely low year for ice cover. You can see more or less the same distributions for ice close to shore both years, but comparing to 2022, you see almost no offshore ice cover at all in 2023, especially for Lake Superior and Lake Erie. So from just these 2 consecutive years of data, you see such a huge difference in ice coverage, which leads us into one of our major talking points for these upcoming analyses, interannual variability. Looking at just the raw time series for ice cover in the Great Lakes Basin, you can see just how much ice cover can vary from year to year. In particular, you can see record high ice years in 2014 and 2015, and likewise an important record low ice year in 1998. This low ice year coincides with the 1998 El Nino event, which was one of the most powerful El Nino events in history and marked a regime shift for ice cover in the Great Lakes. Interannual variability is such a pivotal factor in ice cover analysis, especially with the presence of these exceptionally high and low years. As another way to illustrate interannual variability, here's the basin-wide climatology for the 51-year period, with error bars showing 1 standard deviation above and below the mean. So you can see based on these bars that there is a lot of variability, and especially around the middle of the graph, meaning it gets most variable around the peak of ice cover. This is once again a result of the sheer difference in total ice cover between years, but it's also a result of the differences in the behavior and more specifically the timing of ice growth each year. So in order to analyze long-term trends, we use linear regression to see if there's any significant relationship in the data over the entire 51-year period. For ice cover duration, you can see a pretty clear decreasing trend over the whole period, especially with the period ending on that exceptionally low 2023 season. You can see several other low ice years, including that 1998 El Nino year, and all of these low years are really taking place in the later half of the graph, which would explain why the trend here appears so negative. Here, our AIC shows a very similar result, a trend of decreasing ice cover over time. This analysis utilizes the previously mentioned climatologically filled data, which does make a visible difference for the earliest years of data. Since AIC with the filled data is lower in earlier years, it does flatten the trend line a little, but at any rate, the overall trend here is still one of decline. Because the 1998 El Nino event marks such a turning point for ice cover, we decided to do an additional AIC analysis, separating the data into intervals before and after that point in 1998. And interestingly, when you perform linear regressions for the isolated intervals, you can see that the first interval leading up to 1998 still shows a negative trend, but the second interval actually shows a positive trend following 1998. So these analyses seem to imply that although the overall trend is decreasing, it's possible that ice cover has been on a relative incline since 1998. That being said, we can test for the statistical significance of these linear trends using p-values. Generally, any p-value less than or equal to 0.05 is considered statistically significant, and anything greater than 0.05 is considered insignificant. And based on these p-values, you can see that the AIC analyses for the full period are all statistically significant, but the smaller intervals, unfortunately, are not, likely due in part to the fact that they are simply smaller samples of data. For AMIC, we were able to get an additional data set that extended our period of data by an additional 10 years back to 1963. AMIC, much like AIC, shows a decreasing trend in the maximum ice cover over time. So ultimately, all of our regression analyses for the full period of ice cover data show negative linear trends. And if we look once again at separated intervals before and after 1998, we can once again see the same result as with AIC, a decreasing trend pre-1998, and a sudden increasing trend post-1998. So both this graph and the equivalent for AIC imply the same behavior, with 1998 marking a shift in ice cover to a period of relative increase. Unfortunately, though, if we look at our p-values for AMIC, almost all of the analyses across all lakes are shown to be statistically insignificant, including some of our analyses for the full period, actually. This result seems to signify that AMIC shows a much weaker correlation over the full period compared to AAIC. Overall, there are several key takeaways from this project. All of our analyses showed decreasing trends in ice cover for the full period of data. The table here shows the total percent ice cover loss in each lake over the full period of time based on the linear trends of AAIC and AMIC. And you can see that every lake has a negative trend in ice cover for both analyses. At the same time, all lakes showed extremely high interannual variability across all analyses, which resulted in poor predictability for ice cover. Our results illustrate some of the dangers, so to speak, of using linear models to analyze long-term trends, as many of our analyses turned out to be statistically insignificant. And even for our analyses that are significant, they can really only be interpreted within the period of data we used. So these analyses are not applicable to, say, studies of long-term multi-decadal variability. And lastly, AAIC is shown to be generally more meaningful than AMIC with regard to climate studies. A major difference between the two is that AAIC implicitly includes ice cover duration in its measurement, whereas AMIC really only draws from specific data points. And what that means is that AAIC is more representative of the full span of ice cover in each year. So ultimately, these analyses provide an extensive view of interannual lake ice trends over their respective periods, but further analysis into greater long-term trends and correlation with other atmospheric patterns will be up to future studies. And that is all for my presentation. Thank you.
We've got Michael. Questions for Michael?
Thank you. Very nice presentation. My question is, I know you looked at sort of the whole Great Lakes area with these metrics, but in your wading through the data, did you notice some areas showing more rapid decline or a greater decline than other areas?
Yeah, so one of the things I didn't really touch upon in this presentation was Lake St. Clair. Lake St. Clair obviously behaves very different from the other lakes because it's just so much shallower and so much smaller. So if you look at, if you were to look at the time series for Lake St. Clair, you would see pretty much full ice cover every single year. And Jessica's project will go into some other similarly smaller regions of the Great Lakes, Green Bay and Western Lake Erie, which will have kind of the same behavior, so you can get sort of an idea for that. But a lot of the analyses we performed for St. Clair yielded very different results. AMIC, obviously, the annual maximum was pretty much just a straight line of maximum ice cover over the whole period. So St. Clair definitely differed from the other lakes very drastically, which is why I didn't end up including it in some of these tables here. But other than that, there are similar differences in depth between the other Great Lakes that also contribute to these differences. I believe Erie is another shallower one. So yeah, it does vary a lot with respect to the depth of each lake and the bathymetry specifically.
Just out of curiosity, these are, short-term internships. If you had more time, what do you think you would investigate next? So what, yeah, so what would you like to investigate further?
Yeah, so the main thing to look at moving forward with this data would be addressing those oscillation patterns specifically. So we looked at AMIC and AIC splitting up the intervals with respect to that regime shift with the El Nino Southern Oscillation. Really just kind of like a proof of concept, a way of saying linearly, would we be able to see a change in the behavior of the trend if we just split up the data based on how El Nino changes? But there's definitely stronger correlation analysis you could do directly between, say, these ice cover analyses and the actual analyses of El Nino itself. That would probably provide a much more conclusive result than what we had here. So this really gives sort of really proof of concept, a lot of the general idea of what may drive these trends in ice cover, but without stronger analysis specifically for that purpose, you can't really conclude anything from just this.
It seems like you talked a little bit about the challenge in getting statistically significant results from your analyses. Is that a function of the quantity, the amount of data that you have? For example, you're looking at, in this slide, you're looking at annual maximums. Would a statistical analysis that looked at more temporally frequent data be more reliable potentially? Like if we had data that showed monthly or daily ice coverage. Does that make sense what I'm asking?
Yeah, definitely. No. I think without a doubt, having a greater range of data to analyze would contribute a lot to statistical significance. One of the reasons we say that AMIC is not as conclusive as AAIC is because with AAIC, you're averaging each year ice cover data over a period of time, whereas AMIC, you're pretty much just taking, the one maximum point in each year. So even just the difference between how these two analyses are performed seems to yield very different results as far as statistically significant analyses go. Yeah.
I also have a data question.
Okay.
Since we're on the topic. So you said you were able to add, go back an additional 10 years. You were looking at a 60-year data set, which I think is really powerful. How were you able to go back further in time? Where did you get those additional historical data? And is there any standardization that you needed to do in order to incorporate additional historical data into your data set?
So yeah, we had a data set ranging from 1963 to I think around the 2010s for AMIC specifically. So it had already been in that format for that analysis. And the reason it doesn't exist for, say, AIC is because we didn't have the full daily ice cover data with which we could use to calculate AIC. So that extra data set had already been presented to me in the form of specifically the annual maximums. So that was pretty much the extent of what we could do there.
Yeah, just to that point. So those first 10 years are really before there were consistent satellite observations. So you didn't have daily, I'm just trying to sort of answer your question too. You didn't have like daily coverage or a good view of the entire lake. So a lot of times we sort of discard those first 10 years. Interestingly, I haven't updated it with 2023, but if you look at 73, like when we had good satellite data, the AMIC trends are typically more significant. And you actually have a smaller sample size. So I think that sort of is indicative of the fact that you might need to use caution when you use those first 10 years.
Didn't ask the question well, but that's kind of what I was asking. Great. Okay, we will now move on and thank Michael again for his presentation.
Thank you.